Okay, so it's 7:30 my time, so let's get started. Hello, everyone. Welcome to the second session of week one of the Context in Episodic Memory Symposium International. So good morning, good afternoon, good evening, wherever you are. So this allows us to, accommodate maybe 3 or 4 totally different time zones. So we're very happy so far about how this has gone. So today we have a great lineup of talks and posters. So first up, we will have a keynote by Professor Klaus Oberauer on why is time good for working memory, and that will be followed by several posters. Now, of course, Professor Klaus needs no introduction, but I will still give you a brief introduction. So he is a professor of cognitive psychology at the University of Zurich. And he studies working memory, and he's made several seminal contributions to our understanding of working memory, about the capacity of cognition, about how all of this relates to our ability to reason. And he does this through a combination of careful experimentation and also computational modeling. So it is my great honor and privilege to welcome Professor Klaus Oberauer to share his slides and tell us more about his fascinating research.
Yeah, thank you very much for the nice introduction, and I'm going to share my slides now if I find them here. And do you see this now? Okay, good. Okay, so yeah, welcome everybody. I want to tell you a bit about the beneficial effect of time for working memory. So my apologies, this will be mainly about working memory, not episodic long-term memory, although I will mention episodic memory at a few places. Imagine you're doing a plain vanilla experiment on immediate serial recall of a list of, say, letters. And then you can present these letters either fairly quickly, such as here, or you can present them at a more leisurely pace, such as here. And now in a normal in-presence conference, I would now do a quick audience poll, show of hands about which of these presentation rates you think should lead to better immediate serial recall memory. But this being an online conference, that's not so practical. So I'm just going to tell you that the slower presentation rate leads to better serial recall. Now that is probably not so surprising for an episodic memory researcher, but for people who have grown up in the working memory community, that might be a bit surprising, because working memory research has for a long time been dominated by decay theories. And according to a decay theory, time is the enemy of maintenance. And I think it might be in part due to this dominance of decay theories in our field that the beneficial effect of time for working memory has long been neglected. Although the basic facts have been known for 6 decades now, already in the early 1960s, a number of experiments came out showing that when lists of verbal items are presented more slowly, then immediate serial recall is better. And this is very consistently so, at least for visually presented verbal items. It's less consistent with auditorily presented verbal lists. So with auditory presentation, some found that slower presentation is better, others found that faster presentation is better, some found no effect at all. It's also not so clear what happens when, on top of the immediate serial recall task, people are asked to engage in concurrent articulation. That means speaking aloud continuously some nonsense syllables, such as always having to say ba, 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 ba. This is a technique intended to suppress articulatory rehearsal. And back in 1984, Badley and Lewis published 2 studies actually investigating the effect of varying presentation rate while demanding concurrent articulation. In one of these studies, they found that with concurrent articulation, faster presentation actually leads to better serial recall than slower presentation. And they hailed that as evidence for their idea that memory traces decay once articulatory rehearsal is prevented. Now, in the other study, they did not find that effect. If anything, the effect went in the opposite direction, and they didn't comment on the implications of that in their discussion at all. Be that as it may, more recent research by Ricker and Hartman have shown that also recall of simple visual features benefits to some extent from a more slower presentation rate. Now, I'm mostly interested in why slower presentation, more free time between the items might make working memory better. And we can take from theories about working memory from the extant literature a number of candidate explanations. One possibility is that the time in between items is used for some sort of maintenance process, such as articulatory rehearsal or attention-based refreshing, or even elaboration of the items that people have encoded up to that point. Another possibility is that time in between items is used for short-term consolidation. The idea of short-term consolidation is that this is a process that transforms a fairly fragile sensory representation into a more robust representation in working memory within about half a second to a second. A third idea is that as items are spaced more apart in time, they become more temporally distinctive, and if temporal context is a retrieval cue in an immediate serial recall task, then that should make items less confusable, so that could help. And a final possibility is that slower presentation rate simply gives people more time to gradually also build up representation of the list in episodic long-term memory. And so then at recall, they can draw on two memory representations, one in working memory, one in long-term memory, and thereby recall the list better. Now, in the first part of my presentation today, I want to tell you about 3 experiments varying the presentation rate of verbal lists. And the aims of these experiments were first descriptively just to document the effect of the presentation rate on immediate serial recall over a wide range from very fast to very slow. Second aim was to resolve these remaining empirical ambiguities about the effect, so to determine whether there is actually a beneficial effect of time also with auditory presentation of verbal materials, and whether there is a beneficial effect also under concurrent articulation. And the third aim is to provide a first test of this idea that maybe with slower presentation, with more time, episodic long-term memory contributes more strongly to recall. So the design of my first experiment is fairly simple. I asked people to recall lists of 9 digits or 7 letters or 7 concrete or abstract words. This contrast between concrete and abstract words served to give a hint on whether elaboration might play a role, because I think that concrete words are easier to elaborate. And if elaboration contributed to the beneficial effect of time, then lists of concrete words should benefit more from a slower presentation rate compared to abstract words. Now here I varied the presentation rate list-wise from very fast, 200 milliseconds per item, to very slow, that's 5 full seconds per item. So I didn't want to go even further because people got pretty bored by then. And another important feature of this experiment is that I grouped the trials into mini blocks of 5 trials. And within each mini block, the lists were always from the same material class. So it could be a mini block of 5 lists of digits. And then in the next mini block, I switched to, say, 5 lists of concrete words. And then for the next mini block, switch to 5 lists of letters and so on. And the idea here is that to the extent that episodic long-term memory contributes to people's recall performance, we should see a gradual build-up of proactive interference within each mini-block, and then a release from proactive interference once we switch to a new class of materials in the next mini-block. Because this is how episodic memory works, right? We get this buildup of proactive interference. And if episodic memory contributes more with the longer presentation rates, then we would expect more proactive interference at slower presentation rates. Okay, here's a first view at the results. So this is what I call a time accuracy plot, plotting the proportion correct. So I score these lists by scoring as correct each item that was recalled in its correct list position. And this is plotted here over presentation time per item. And you see that for all 4 kinds of materials, serial recall gets better with slower presentation rate, with a fairly sharp initial rise and then a more gradual monotonic increase of performance with slower presentation rate. And you might also notice that when you compare the concrete and the abstract words, concrete words in green, they do seem to benefit more from longer time than the abstract words. So that might be a hint that elaboration does play a role here, at least for the words. Now here's a more fine resolution look at the same data. These are serial position plots. So on the x-axis, we have the serial position in the list. And now the presentation rate is coded by the color of the lines. And one thing that stands out here is that the beneficial effect of slower presentation tends to grow towards the end of the list. So for the first 1 or 2 list items, the presentation rate has hardly any effect, but then for later items in the list, it becomes an increasingly big effect. And this is true for all 4 kinds of materials. I'm showing you just 2 of them because they all look qualitatively the same. Now, this is already an important finding, because if we think of this first kind of explanation, that people use the free time in between items for some sort of maintenance process that might strengthen the memoranda, then we would expect that the early list items would benefit most from longer inter-item interval, because every single inter-item interval can be used to, again, rehearse or refresh the early list items. So the early list items get many more inter-item intervals in which they could be strengthened by some maintenance process, compared to the last list items, which have hardly any inter-item intervals following them, during which they could be strengthened. So if maintenance processes are involved, are responsible for the free time benefit, then we should, if anything, predict the opposite pattern, with a larger benefit early in the list compared to later in the list. Now, let's have a look at the effect of proactive interference. This is now plotting presentation accuracy over the position of a trial within a mini-block. And proactive interference would be noticeable here as a gradual decline over mini-blocks from the 1st to the 5th trial. And that is just not what we see, not even for the slowest presentation rate. There is no hint of build-up of proactive interference in these data. So I conclude from that that episodic long-term memory does not contribute in any meaningful way to performance in this task, and therefore cannot explain why more time leads to better memory. Okay, the second experiment is pretty much the same, except that now I presented the stimuli in a spoken auditory format. And because I wasn't quite confident that people would really understand the spoken words at these very fast presentation rates, 200 and 400 milliseconds, I started only at a slower presentation rate. So I left those 2 out. That's probably why we don't see in the data and the time accuracy functions this very sharp rise of accuracy over the shortest presentation times, because we don't have them here, but still we see a fairly clear monotonic increase of performance over increase in presentation time per item. In this experiment, again, I see no hint of proactive interference. Here's again serial position curves for 2 of the kind of materials, and we see the same pattern again. The presentation rate has hardly any effect for the first 2 or 3 items in the list, but then towards the middle and the end of the list, slower presentation rate becomes better. Now, the third experiment is again like the first visually presented lists, but now in half of the sessions, participants were asked to engage in concurrent articulation during presentation of the lists. And because concurrent articulation is known to substantially decrease serial recall performance, I now shortened the list to keep the task still doable for people. And so here you see the time accuracy plots again on the left side for the quiet sessions replicating experiment 1, and on the right the sessions with concurrent articulation, and you see a substantial drop in performance, but still slower presentation time translates into better memory. The effect of time is hardly diminished, with the exception of the abstract words. So, to conclude this first part of my presentation, we see across all these experiments a beneficial effect of free time between items on immediate serial recall. We see that this benefit accumulates towards the end of the list, and that makes it unlikely that any sort of maintenance process in between list items is responsible for the beneficial effect. We see that the effect is hardly diminished under concurrent articulation, so articulatory rehearsal certainly has nothing to do with it. We saw across all 3 experiments that the beneficial effect of time is larger for abstract words, larger for concrete than for abstract words. And in fact, with articulatory suppression or concurrent articulation, there was no effect for abstract words at all. So that might be a hint that elaboration does play a role in this effect. But then on the other hand, digits and letters also benefit just as much as concrete words from more free time. And I think digits at least are not easier to elaborate than abstract words. So I think elaboration cannot be the full story. And again, elaboration is one of these maintenance processes that would have to increase, if anything, the earlier presented items more than the later presented items. So I don't think that that's a very plausible explanation overall. Finally, we saw no evidence for proactive interference in all these experiments, and so episodic long-term memory is unlikely to be responsible here for the beneficial effect of time. Now, in the second part of my talk, I want to tell you about research that I've been doing together with Eda Misrak, who you can see here in the upper right corner. And this is now one experiment that we designed specifically to disentangle these candidate explanations that I introduced at the beginning, these candidate explanations for the free time effect. And to appreciate the rationale of this experiment, I invite you to consider a very simple manipulation of just one inter-item interval, say the interval between the 3rd and the 4th item in this list up here. Imagine you make just that interval longer in an experiment. Now we can ask, okay, this is giving people more free time in between these 2 letters, and we can now ask, which of the letters of the list benefit from this free time? The benefit could be retroactive, that is, it could be a beneficial effect of free time on earlier encoded items, or it could be a proactive effect, beneficial for subsequent yet to be encoded items following that free time manipulation. Or of course it could be retro and proactive in both directions. Independent of that direction, we can ask whether the effect is global, affecting all the preceding and or following items, or the effect might also be more local, limited to the one item preceding or following the interval that we manipulated. And that gives us a matrix of 6 possible combinations of effects, and we can now sort our candidate explanations into the cells of these matrices, depending on what pattern of benefit of free time they predict. So thinking again of the idea that maintenance processes such as rehearsal or refreshing are applied in between items, maintenance processes logically can only be applied to items that we have already seen and encoded. So this would have to be a beneficial effect that's retroactively benefiting earlier items. And because all these maintenance processes are conceptualized as covering all the items that we have currently in working memory, the predicted effect would be global. So that would be a benefit for all the items preceding an interval that we extend. Now, thinking of the idea of short-term consolidation as one explanation, we need to distinguish two versions of that idea. In one version, short-term consolidation would be interrupted by the onset of the next stimulus. So if you imagine you start short-term consolidation of the letter Q, and then you have only a short interval following the S, the next letter coming on very quickly, then the short-term consolidation of Q would be curtailed very early, whereas if we extend that interval, then Q could be fully consolidated. So on that version of short-term consolidation, it would be the one letter immediately preceding an interval that would benefit most from expanding that interval. So that would be a retroactive local effect. But then there's also the proposal by Tim Ricker, for instance, that short-term consolidation is ballistic. And the idea here is that once you start short-term consolidation of that letter Q, that runs to completion. And if now a next stimulus like S comes up very briefly after, then consolidation of the S would just have to be postponed. And sometimes it's postponed so long that it's never going to be consolidated at all. And in that scenario, this ballistic short-term consolidation, a short interval between two letters would be detrimental for the item following that interval. And if we now make that interval longer, it would be the one item immediately after the interval that would benefit because it has a better chance of getting into the consolidation pipeline. So that would be a proactive local benefit. Now, the temporal distinctiveness account, the idea here is that when we space the letters Q and S further apart, then that makes these two letters more distinctive, more less confusable on the time dimension. So that would be an effect that's both retro and proactive, but it's local. It's mostly concentrated on those two letters immediately bounding the manipulated interval. Finally, this idea that encoding into long-term memory plays a role, that would again predict a retroactive effect, because when we have a long time between two items for encoding information into long-term memory, then only information that you have seen so far can be encoded. And if that encoding into long-term memory pertains only to the last presented item, then it would be a local effect. But you could also think it might be a global effect if everything that you have in working memory is encoded into long-term memory once you have some time for doing it. Okay, so that's the rationale of the next experiment. And I think you can probably already guess the basic design of that experiment. It's again immediate serial recall of lists of letters, 7 letters. And we have 3 basic conditions. In the baseline or control condition, we present the entire list at a relatively rapid, constant pace of 550 milliseconds per item. And then we have 2 gap conditions, a so-called short gap condition, in which one of the inter-item intervals is expanded a bit to 1 second, and that interval can be anywhere in the list. And then we have a long gap condition, where again, one interval anywhere in the list is again expanded, but this time much more, 2.5 seconds. Right. So to illustrate, at the bottom here, we have one example on the top here, the BFQ, that would be a control condition. So all the inter-item intervals are the same. And then we have 3 examples of gaps after the first, after the second, or after the third item, and so on. So the gap position was systematically shifted through the list across trials. Now, the reason why we had a short gap and a long gap condition is that just introducing a gap, a temporal gap somewhere in the list, causes temporal grouping of a list. So people's representation of the list is broken down into two groups at that gap, and grouping in and of itself is known to improve immediate serial recall. But that is not the effect that we were interested here in. We were interested in the additional effect of expanding the gap interval from 1 second to 2.5 seconds. Unfortunately, the grouping effect doesn't depend on how long the temporal gap is, as long as it's noticeable. And so we can use the contrast between the short and the long gap to gauge the beneficial effect of time per se. Okay, and here's the main results. Each panel gives you the serial position curve for the short gap condition in blue and the long gap condition in red. And in each panel, we have the data from a different location of that manipulated gap or inter-item interval in the list. And where the gap was is denoted by this vertical broken line. So here, for instance, we have a gap between the first and the second item. And now throughout all these different gap positions, we see that a longer gap, so longer free time, is beneficial for the items following that gap. So it is a proactive effect. We see no hint of a retroactive effect when we average across all 6 gap locations. And the beneficial effect extends to all the items following the gap. So it is a global proactive effect. Now, that was, at least for us, quite surprising because it doesn't match any of the predictions of any of the explanations of free time benefits that are on the table so far. Right? And so at that point, we had to scratch our heads a bit and come up with some post hoc explanation for our findings. And the best explanation we could come up with so far is one that we borrowed from work by Van Popov and Lynn Reeder on episodic memory, for which they proposed that encoding an event into episodic memory requires a limited resource that is then partially depleted by that encoding process, but then afterwards that resource is gradually replenished again over time. Right? And so we borrowed that hypothesis and applied it to working memory, and we formalized it in a very simple way, assuming that participants start each trial with a full pool of encoding resources. So that would be R1, which we just set for convenience to 1. And then we assumed that every item is encoded by recruiting a constant proportion P of the encoding resource Ri that's available for item I. And the amount of encoding resource that is then assigned to that item becomes the item's strength, Si. Right? And then, of course, there's a residual resource, Res, which is then the proportion 1 minus P of whatever resource Ri we had available for encoding that item. Right? And then in the free time following encoding of item I, the resource is gradually replenished as a function of time. So we compute the resource available at the onset of item I plus 1 as the residual resource, Rs, plus some addition, some replenishment, top up, that's a gradual, negatively exponentially growing function of time. And with this model, we can then simulate memory strengths in an experiment like the last one that I've just shown you here with the 2 conditions. The black lines is a condition just without any gap, and the red lines, that's a condition with a gap here, for instance, between item 3 and 4. And because a longer gap between item 3 and 4 means that at this point, the encoding resource can be replenished more, that means that all subsequent items start being encoded with a higher level of resource, and that benefits all of them. This idea also naturally generates a primacy gradient, as you see, because with each item, the resource, the encoding resource, is replenished to some extent, and the time in between items is not enough to fully replenish it. And we can also use the same model to simulate the earlier experiments, where we then see that, yeah, more free time in between items leads to better memory because it allows more recovery of the resource. And that interacts with serial position in the way that we saw in the data, because especially towards the end, it becomes important to have longer intervals between items to replenish the resource. Whereas at the beginning, the first item always starts out with a full resource pool. So for the first item, according to this idea, doesn't matter how long the inter-item intervals. Okay, and that brings me to the end of my story. I hope I have convinced you that free time between items does improve immediate serial recall of at least verbal lists throughout a fairly broad range of conditions. And all the common explanations are probably wrong. So it's nothing to do with maintenance processes. It's not due to short-term consolidation. It's not due to time allowing encoding into episodic memory. Temporal distinctiveness is also not responsible. So the one candidate explanation we currently know of is that an encoding resource might be involved that is depleted by encoding and then uses inter-item time to be gradually, partially replenished. Thank you for your attention.
Right. Thank you very much, Professor Oberauer. And so I think we have time to take maybe 2 or 3 questions. So let's open up the floor. Please go ahead, Devon.
I think Jeff.
I have a question. Really nice talk. Really enjoyed it. I think your data are fantastic. I think the manipulations you've done are really fundamental to our understanding. I'm not sure I totally agree with your interpretation always, but that's what science is about. I really love the data. I was just wondering, you concentrated on a couple of things. You said you ruled out a lot of interpretations, some of which I would prefer. I have kind of like 2 minor queries. You throughout the talk quite rightly spoke about immediate serial recall with immediate serial recall scoring, with serial recall scoring. Do your data patterns hold for recalling the items? So if you had like a free recall scoring system, I'm just thinking that one of the reasons why you might do well in a performance after a gap might be that you have correctly filled up the items before the gap. So in order to score an item correct in its correct position, so for example, the 4th item in its 4th position, that's easier if you've correctly recalled the first 3 items. So I'm just wondering whether that the later items benefit because you have because you're more able to put them in the right position. But there might not be so much of a difference in free recall, for example. And I'm also interested just generally whether the free recall, the items scoring with free recall, whether this will tell you something about the mechanism for the improved performance in serial recall. It's just interesting to see whether the free recall scoring mirrors the serial recall scoring or whether it's independent. I think logically it could be either.
Yes. Well, I haven't looked at free recall scoring of these data, primarily because for the digit lists, well, item errors cannot be made because in a 9-digit list, all 9 digits are used. Right? But the letters, again, I don't expect too many item errors. With the words, that would be interesting. But yeah, I can't really say whether the results, especially the results of the 2nd experiment, whether they hold also for free recall scoring. Haven't looked at that yet.
Well, if ever you're willing to share the data, I'd be delighted to have a look at it.
Yes, sure. I think the data of the second experiment should be online on OSF actually.
Fantastic.
Because that paper is published.
I think that Deborah had a question.
Yeah, hi. I thought the lecture was extremely thought-provoking, really, really interesting. Thank you very much, and also extremely clear. Could you, the one thing that was left a bit mysterious is the nature of this encoding resource.
Mm-hmm.
So you mentioned that you borrowed it from the literature on episodic memory. I'm not familiar with that work. Does it apply conceptually exactly the same to working memory? What is this thing?
Yeah, that's what I would like to know, and that's why I'm personally not fully satisfied with this explanation, because in my view, the idea of a resource is, basically something. It's basically pointing at something that we don't fully understand yet, right? The only thing we can say about it is it's limited, it's depleted, it's replenished, but of course it's not a mechanistic explanation of what's going on. And so, yeah, I'm currently exploring mechanistic models of working memory, connectionist models, and trying to identify something there that that we could, by which we could spell out this this idea. But at the moment, yeah, this is still work in progress. I can't say much about it yet. But eventually, we will have to cache that out somehow mechanistically. And whether then it turns out to be the same for working memory and long-term memory, maybe yes, maybe no. Of course, I prefer an explanation that applies for working and long-term memory. That would be the simpler story, but it could well be that we have different mechanisms that just on a global level behave in a similar way.
I think we have we can take one more question.
Mm-hmm. Hi, Aaron.
Hi, thanks for the wonderful talk. So I was not familiar with that paper from 2020 you mentioned, but there is one mechanism, cognitive mechanism, which we can call resource, and we know is important for encoding in working memory and LTM, and that is attention. So I was wondering if what we call resources can be simply attention, but then I'm not sure if it explains the fact that we don't see retrospective but only prospective effects, because if attention is still involved in processing the former item before extending the gap, then extension should also benefit the item before, not only after. So that part is a bit confusing. But apart from that, maybe it might be fruitful to use a term that we agree a bit more. But yeah, I would like to hear your opinions on both of those points that I raised.
Yes, I think you could tell a story by which attention is somehow gradually diminished by encoding more and more items into working memory. And then if you assume that attention is always focused on the next item to be encoded and does not go back to earlier items, then that could work. I'm not sure everybody agrees that attention is a resource, though. For instance, I'm not quite convinced of that actually. But even if everybody would buy into that, I'm not sure we gain anything from relabeling this as attention, unless doing so comes with additional implications, testable implications. Off the top of my head, one might be that if we distracted attention in between an item and the next, that would make memory for the next item even worse, because we deplete the attention even more. And I guess at that point, we need to then talk about which kind of attention we're talking about. Like, for instance, we could distract visual spatial attention by a visual search task in between an item and the next, and I bet that wouldn't do anything for subsequent items. But we could also think of more central attention, like attentional bottleneck, asking people to make a decision. And I could imagine that could be damaging for subsequently encoded items, something we should probably try at some point.
All right. Thanks again, Dr. Klaus, for that fascinating talk and for addressing all these questions. I think we still have some questions in chat. So if you have the time, if you could respond in chat. So let's thank our speaker again.